Hello again, my dear students. Now it's our final chapter in this course, in the electronic course, Electronics 1, delivered for year 1 after prep electrical engineering department, electrical and communication program. It's our last chapter, the terminating chapter under the name of operational amplifiers. If you remember, we have we go together into three main chapters in this course or in this module. We start with the p-n junction die, then we go to the metal oxide field effect transistors, or what is abbreviated by MOSFET. And in chapter 3, we deal with what's called the bipolar junction transistor, or the BJT. Now it's lecture number 4. We are going to deliver this lecture into 2 successive academic weeks. We will start by 50% of the content today through 2 video lectures, part 1 and part 2. And in the next coming week, in week 11, academic week 11, we will terminate our course, our module, by the remaining 50% of this lecture. So let's now start our lecture under the name of operational amplifier. Okay. Let's first start about some microscopic view, some big image of what we are doing. If you remember in the solid state electronics course, and maybe in the beginning of our previous 3 lectures, when we were dealing with p-n junctions, when we were dealing with MOSFET and BJT, we usually were interested about the structure of the device, or energy band diagrams, schematics, charge, carrier transport, carrier concentration, and all this stuff, if you remember. We fulfill one module, one complete module in order to understand these structures, or what I can say is this physics. It was something, what is inside the device, what is inside the BJT, what is inside the MOSFET. From an electronic point of view, we call this as a sub-transistor level, where you are dealing with the internal structure of the transistor, either a MOSFET or a BJT. As a next step in this module, we transfer from this transistor level, or from this sub-transistor level, to what we can call the circuit level, or the transistor level. We start to construct circuits based on our transistors, either MOSFET or BJT, in order to functionalize some functions, like when we use our MOSFET, our common source configuration, as an amplifier, when we demonstrate the use of the MOSFET as a switch, and when we use the bipolar junction transistor as an amplifier as well. So this is what we can call a circuit level, where you make a transistor level, where you make your circuit based on a series of transistors, either MOSFET or BJT. You connect these transistors together to construct some function. Now, in this lecture, and maybe in many coming modules, inshallah, you will turn to a third higher level, or what we can call the IC, which is the integrated circuit, or the gate level. I believe you already did this in the digital design course, when you deal with these logic gates and you start to construct your circuit using this gate level. Now we will do the same. Now we will go on an upper level. We will leave the sub-transistor level. We will leave the transistor level, and we will work with an IC, or what we can call a gate. In digital electronics, you are dealing with what we can say, or what we can call a digital gates, the digital logic gates. Now we have another type of gates. We have what's called the operational amplifier, which is some sort of an IC that used to functionalize certain functions or certain operations based on certain conditions that we will try to understand during this lecture. So, what is inside this IC? What is inside this operational amplifier? Simply, it's a huge number of transistors. So in order to construct an IC, in order to construct an integrated circuit, you have to combine, You have to combine a huge number of transistors by some sort of another. You have inputs, you have outputs, and then you have a complete integrated circuit. Your digital logic gates have the same manner as well. It's a huge number of transistors connected together and construct the NOR function or the NOT function or the AND function or the OR function or whatever the function you need. But when you are dealing with the gate level, you are not interested with this schematic. You know that you have an AND. This AND do some function. What is inside the AND is basically a black box. You are not interested in it. So when you are dealing with a gate level or an IC level, you are not interested with what is inside each IC. You just have a circuit, you just have a block. This block do some function. You use this block to make some sort of operation. That's all. What is inside is not my business. So in this lecture, we will deal with this with this operational amplifier. We will not go into the details how this function has been constructed. However, maybe in later courses, advanced courses, senior H-level courses, you will be more interested to understand what is inside. But now, we will not be interested to do so, and we will only deal with the input-output relationship without going into details. So, what is the IC in the reality? Maybe many of you see integrated circuits before. Simply, if you see a motherboard or any device, you will see this integrated circuit. So this is an IC where you have a packed IC, you have a terminal here, and then you connect the terminals to get inputs and outputs and so on. This is a very famous shape. Most of you maybe already deal with or see it somewhere. So this is the IC or was the integrated circuits. Let's now go to our device. Again, what we are going to do is that we are now interested to make some relation between inputs and outputs. So in order to make these relations between input and output, you have first to define what is your input and what is your output, or what are your inputs actually, and what is your output. As you can see in this operational amplifier, we have very interesting 5 terminals. First, we have what we can call the biasing terminals or the supply terminals. These are the supply used to operate the device. This is the supply used to operate the transistor inside. In order to make this more clear, let me return to this circuit. I believe you already studied this circuit in our lecture number 2 in the MOSFET. Here you have an input and here you have an output. But in order to make a relation between the input and the output, a DC biasing is needed, what we call here a VDD, which is a volt applied to a drain through the resistance. So without this VDD, you will not have this input-output relationship. So usually we should have a DC biasing, we should have a DC supply in order to operate our MOSFETs. Either they are our MOSFETs or our BJT. If you remember, in the previous lecture, we connect usually what's called the VCC and the negative VEE. So one is connected to the collector and the other is connected to the metal. So these are the needed DC biasing, the needed DC supply in order to operate our transistors. So again, here are these 2 terminals. This is the positive supply, which is simply the VCC, and this is the negative of supply, which is simply the negative VEE. So we just connect to these 2 terminals together. Oh, sorry, connect these 2 terminals to supplies, a positive terminal and negative terminal, and then we start to work with the operational amplifier. Maybe in this part of the lecture, we will not be so interested about these 2 terminals. Maybe in the second part, we will be more interesting about that. But let's now skip to the next point, which is what is the input and what's the output. Here we have 2 types of input. We have what's called the V1 or the inverting input. We will be very interesting to know why we call this as an inverting input. This will be actually delivered in this lecture. So this is an inverting input and this is a non-inverting input. So we have 2 terminals. These 2 terminals are connected to the operational amplifier. The first is called the inverting, which has a negative sign, and the second is called a non-inverting, which has a positive sign. So as you can see here, this is the 2 terminal. Here is the input resistance of this operational amplifier. I believe we already focus on this input resistance while we are dealing with the MOSFETs or the BGT amplifiers. So you should know what's mean by input resistance. Then in the output terminal, you have one output terminal. Here, this is the output terminal. You have an output resistance. We call it Z out. And as you can see, the input and the output are related by this voltage controlled voltage source. The input, the output is simply the difference between the input, V2 minus V1, multiplied by what we can call an open loop gain. So this is the open loop gain. I'm sorry, this is a typo mistake. So this is the open loop gain. I will modify it in the presentation. I'm sorry for that. This is the open loop gain, not the closed loop gain. So this is the open loop gain is simply the A, which is the open loop gain. Let me fix it now. So I'm sorry for this type of mistake. So this is the open loop gain. So simply the output is the difference between these two input terminals multiplied by some gain, which is the open loop gain. So this is a very important point to understand, because maybe 1 or 2 slides later, we will go into details about what is the open loop gain. So let me repeat again. We have 2 inputs, one called an inverting input, V1, one called a non-inverting input, V2. We have an input resistance, Zin. We have V output. We have a input impedance, Z out. The relation between the output and the input is simply that you differentiate, or you subtract V1, V2 minus V1, the positive minus the negative, and then you multiply this with the term A, which is the open loop gain, which represents the gain factor, the open loop gain factor. So this is the relation. This is the operational amplifier, and this is what we can call the open loop gain. But now let's turn to the next slide. Okay. We have what we can call an ideal operational amplifier. So this is the previous one was the real operational amplifier, the real operation of operational amplifier. But in order to make this operational amplifier more simpler in the analysis, we can deal with what's called the ideal operational amplifier. Let me say that in 99% of our cases in our module, we will have an ideal operational amplifier, not a real operational amplifier, just to make that calculation and the mathematical calculation easy. But what is the difference between the real operational amplifier and the ideal one? Now, this is the ideal operational amplifier. Then, in the ideal operational amplifier, you will find that the resistance here is equal to infinity. The input resistance is equal to infinity. This is the first thing. The second issue is that this Z in or Z out, the output resistance is equal to 0. So one factor in the ideal operational amplifier is that you have an infinite input resistance and you have a 0 output resistance. That's what we can call an ideal operational amplifier. Is that all? The answer simply is no. We still have another important assumption that we will study it after a few seconds, I think. Now, before going to this assumption, let's do the first exercise with this operational amplifier. Now, as you can see, I connect the positive terminal, which we call the non-inverting terminal, this is V2. I connect V2 to the ground. I connect V1 to a resistance called R1 and then to an input voltage Vin. And again, I make this connection. I connect the output to the V1, which is the inverting input, through a resistance called R2. This is the first schematic. And we will call this schematic event the inverting configuration. It's called the inverting configuration for 2 reasons. The first reason, we will have it now, that now the input is connected to the inverting input. The non-inverting input is grounded, so the input is connected to the inverting input. And there is another important reason that we will know it in the next slide. But now let's turn to the point, the ideal operational amplifier. As I mentioned, the ideal operational amplifier is the amplifier which have an infinite input resistance and a zero output resistance. But as I mentioned, this is not only, we still have something else. What if? Now, as you can see, the output is the input multiplied by some gain. The output is the difference between the input, which is V2 minus V1, multiplied by a gain, which is A. So simply V out equals A times V2 minus V1, especially when this Z out is equal to 0. So simply the output is equals to the gain multiplied by V input, which is the difference between these 2 points, V2 minus V1. Okay. What if this gain is very high? Okay, that's great. Yeah, we have a high gain, no problem. But what if this gain is equal to infinity? What if this gain is equal to infinity? When this gain is equal to infinity, then you will have an output equal infinity, because simply V output equals A times V input. So V output equals V input times infinity, which is simply equals to infinity. But realistically, we have an output. Our output is not equal infinity. We should have some voltage in the output. So the condition is, in order to make this A equals to infinity, we should have either V output equal to infinity or V input is equal to 0. Because simply the A is V output over V input. In order to get A equal to infinity, that simply means that either V output equal to infinity or V input is equal to 0. So let's start to think about it. What does it mean that V output equal to infinity? Well, it does not mean nothing, because you get a very, very high voltage, which is infinity, doesn't has an unrealistic mean. But can V input equal to 0? You can simply say yes. Okay, V input is V2 minus V1. So if V2 and V1 are equal, then V input is equal to 0. So this can be implemented. You can put the voltage difference here equals to 0. You can put V2 and V1 equal. If you put V2 and V1 equal, then you will have an input 0, and then the gain will be infinity with finite output, because any value over 0 is equal to infinity, which is typically the gain. So in an ideal amplifier, we will have 3 very, very, very important assumptions. The first is Zin is equals to infinity. The input impedance is equal to infinity. The second is Z out is equals to 0. The output impedance is equal to 0. And the third is the gain is equals to infinity. When a gain is equals to infinity, that means that the V input is equal to 0, which is V2 minus V1. And simply, this means that V2 is equals to V1. So, whenever you find the word ideal amplifier in any problem, you should make very basic 3 assumptions. Infinite input impedance, 0 output impedance, and the 2 voltages across the 2 inputs are equal. V2 is equals to V1. So these are 3 very important assumptions in order to solve your problem whenever you have what we can call an ideal operational amplifier. Now, let's turn to solve this issue. Okay, what is the question? We have this schematic diagram. We connect this with ground, we connect this with input, and we have out. What we are interested in now, we are interested to calculate the relation between V output and V input. Okay, let's start to do it. So now you should make use of your inputs, or you should make use of your assumptions. We have 3 assumptions. Let's start to think about these 3 assumptions. The first is, we say that this impedance, let's do it here. Okay, we say that this impedance is equal to infinity. This is an open circuit. So, is there any possibility to have a current here? The answer simply is no, because whenever this is an open circuit, no current can flow in this circuit. So, that means that the current flowing here and the current flowing here is ideally equals to 0. No current flowing here in this branch, and no current is flowing in this branch. Why I said so? Because I am assuming that this is an ideal amplifier, operational amplifier, and then the input impedance here is equal to infinity. No current will flow inside the operational amplifier. This is the first issue. Okay, what is the second issue? You told us now that as far as it's an ideal amplifier, we have to assume that the open loop gain is equal to infinity, and then we can assume that V2 is equal to V1. Great. So we know that V2 is equals to 0. We know that V2 is grounded. Then what will happen is that we will call this V2, or we will call this point as a virtual earth or a virtual ground. Why we call it a virtual ground? Because basically this point is not connected to the ground. This non-inverting input is not connected to the ground. However, because this terminal is connected to the ground and the voltage V1 equals the voltage V2, then this point should have a 0 voltage, and that's why we will call it a virtual earth or a virtual ground. So this is a very important definition in our circuits, in our operational amplifier circuit, that whenever you have one terminal connected to the ground, the second terminal will be automatically equals to 0 voltage, which we will call it a virtual ground. Now, as I mentioned earlier, no current is flowing here, no current is flowing here. So you can easily assume that the only way for the current is that the current should flow in this direction. Because when the input current is reached this point, which we call it X, no way that the current will move here, because this is an open circuit. That means that all the current will move here and go to this R2 and go then to the output. So this is the only flow of the current between the input and the output. So simply, this is how the operational amplifier works. Now it's very easy to understand or to get a relation between V input and V output. How should we make it? Let's start. Let's start with this branch. In this branch, you have this node is called V input. And this node is called V2 or V1 because both are equal and it's 0. So simply the current flowing here, which is IN, is equals to V input minus 0 over R1. Again, it's V input minus 0 over R1. This is the current flowing in this resistance. So what about the current flowing here? Again, now we assume that the direction of current is in this direction. So the current flowing in this resistance is V2, which is 0, minus V out over R2. Again, 0 minus V out over R2. And you say that IN should equals to this IF. So we can easily equate these two equations. Let's see. So first, the input current IN equals to V input minus V1 or V2, because both are equal, over R1. And we know that V2 or V1 is equal to 0, so simply I1 is equals to V input over R1. What about the second current? The voltage here is equals to this voltage, which is V1 minus I2 times R2. So simply V out equal minus I2 times R2, because this V1 is equal to 0. So V out equals minus I2 over R2. Let's make it again. The voltage here is 0 minus V out equals to I times R. So V out will equals to minus I2 times R2. And then you will have V out equals to V in over R1 times R2. And the relation between V output and V input is equals to minus R2 over R1. Very simple like that. By the way, I will repeat this example in the part 2 using my pen and paper step by step. If you did not understand it well now, you will have another chance to understand it in part number 2. So again, we start by saying that this V1 is connected to the ground. We say that V1 is equal V2. So this is a virtual ground. The current flowing here is V input minus 0 over R1. The current flowing there is 0 minus V output over R2. The current here is equal to the current there, and then we get this relation. Now V output minus V input is equals to minus R2 over R1, and this is what we call the closed loop gain. So as you can see, we have two types of gain. We have the initial open loop gain, which is the initial gain of the operational amplifier, which we assume that it's equal to infinity in case of an ideal operational amplifier, and then V2 should equal to V1. Accordingly, when we start with this this inverting configuration, we found that there is another relation between the V output and the V input, which is the closed loop gain, and this is a finite gain. It's not equal to infinity, and this is equal minus R2 over R1. Now, the final stage here is that this negative sign. Basically, this negative sign is come from the flow of the current, because we assume that the current is flowing in this direction. So it's 0 minus V out equals IF times R2. So that means that the relation between the output and the input include a negative sign. That means that V output equal minus the gain times V input. That's why we call this configuration as an inverting configuration, because simply the output is the inverted sign of the input. If you have a positive voltage in the input, you will get a negative voltage in the output. If you have a negative voltage in the input, you will get a positive voltage in the output. That's why we call it an inverting configuration. Now, let's turn to two issues related to this operational amplifier, or to this configuration. The first issue is, what if the gain, the open loop gain, this A is not equals to infinity? If you remember, we say that for an ideal amplifier, we have three assumptions: infinite input resistance, zero output resistance, and infinite gain. What if this gain is not equal to infinity? So you cannot say that V2 is equal to V1. V2 is equal to V1 only if the gain is equal to infinity, if the open loop gain is equal to infinity. But now what if the open loop gain is not equal to infinity? Then you will have to drive another formula for G. Actually, this is not required from you. I just mentioned it in the script, but I will not require the mathematical analysis from you. But it's very important to mention that as the gain is not equal to infinity, that means that V2 is not equal to V1, and accordingly, you cannot say that this is a virtual ground. So whenever you have gain, open loop gain is not equal to infinity, V2 will not equal V1, and this is not a virtual ground. Accordingly, we will have a new relation to V out minus V in, which is in this form. What is interesting is, if you put here A is equal to infinity, if in this relation you assume that A is equal to infinity, then simply 1 over infinity is equal to 0, then you will get right from this term, and then G equals to minus R2 over R1, which is exactly the same here. So you can say that this is a general solution, which we will not use it, and this is the specific solution, or the assumed solution. When A is equal to infinity, you will have this relation. So now we deal with the first issue, which is the effect of finite open loop gain. What is the second issue? What about the input impedance of this structure? Basically, when we have a structure like, we don't have a structure like that, we can say that the input impedance is equal to 0. Is equal to infinity. Why the input impedance is equal to infinity? Because the impedance is equal to the voltage over the current. Here we have a voltage, but we have a 0 current. So simply the impedance is equal to infinity. That's true. But what about this? What about this structure? Here is the input. This is the input you apply, and this is the current. Okay, here we have an output, so here we have an input impedance equals to 0, that's true. But you have another current is flowing there in this direction. So simply, the input impedance here, or the input resistance, is V input over I input. That's very simple. This is V input over I input. And I input is not equal to 0 because you have a current flowing in this branch. So I input is equals to what? I input is equals to the voltage difference over the resistance. So it's a V input minus 0 over R1. So it's simply V input over R1. So you have V input over R1, which is R1. So Rin is equal to R1. And this is a very, very, very important issue, because ideally speaking, when the operational amplifier is looking like that, this is we call an open loop configuration. You don't have or your input impedance is equal to infinity. But whenever you connect it in this manner, and here we will call this branch as a feedback branch, because it feedbacks the output to the input. Whenever you have this branch, then you have an input impedance, because simply, if this branch is not exist, then the current flowing here will be equals to 0, and then the input impedance will be equal to 0. But what, it will be equals to infinity. But what makes Rin is not equal to R infinity is that you have this branch. This feedback branch, or what we can call the closed loop or the feedback loop operational amplifier, makes that Rin is not equal to infinity and Rin equal R1. And when R1 is small, this will make a very big problem for the operational amplifier. So now we have a drawback of this configuration. The main advantage of this configuration is that we have a gain, and you can control the gain by controlling the relation between R2 and R1. But the disadvantage of this configuration is that you have an input impedance not equal to infinity and equal to R1. In part number 2, we will make 3 very important examples. First, we will start to solve this problem as an example. From the first impression, it's something how like this configuration, because now we have the input connected to the inverting amplifier, you have the non-inverting amplifier connected to the ground, and you have a feedback resistance. But now this feedback resistance is not only one resistance, it's a 3 resistance connected in this configuration. So this is what we will first do. Then we will go to solve another circuit, which is called the weighted summer operational amplifier. And finally, we will go to what's called the non-inverting configuration, when the input is connected to the non-inverting terminal, not to the inverting terminal. So in part number 2, my dear students, we will have 3 main tasks. First, solving this example. Second, making the weighted summer circuit. And third, doing the non-inverting amplifier. But as I mentioned, and in order to make you more and more understand, I will repeat first this issue by step-by-step handwritten in order to make you more and more understand, and then I will go to the other 3 points. So thank you very much, my dear students. I'm waiting to see you in the next part of this lecture. Thank you, and see you later.